Okay, so in chapter 16, we're still studying motion dynamics, but we're going to look at some things that are a little different from what we've done so far. We're going to be looking at rigid bodies, and for now, just restricting them to a plane or planar motion. So basically, sometimes you have some sort of object and you can't really treat it like a particle. Up to now, we really have been doing that, even though we have a box sliding down an inclined plane. We're not really thinking about the dimensions of the box. We're really just sort of thinking about how its center of mass moves. Therefore, we're treating it as a particle. But as you get into more practical aspects, that's not really going to work. So if you're thinking about some sort of gears that are connected to each other or linkages where there's motion about some sort of pivot point, you really have to think about the rigid body itself and be able to analyze that motion. And so we're starting to learn about that in this chapter. So a rigid body basically is a body where all the pieces of the individual, like little aspects or little pieces of it, don't move relative to each other. It maintains its shape. Pieces of the object maintain their relative distances to each other. It doesn't deform, or it maintains its shape. That's what our rigid bodies are. And we're also going to talk about planar motion. And planar motion is when all the body moves along a path that's equidistant from some fixed plane. So basically, we want it to move in a plane. Sort of. There'll be one little add-on to that. So here, just showing some examples of the type of motion that you might be able to understand when you learn the material in this chapter. For instance, this amusement park ride, the people are undergoing translational motion, but it's in a curve because they're going in a circular path, but they always will stay upright. And so, like, for instance, the type of things we'll be able to do is, if the motion of the rotating arms, like if you know how they're moving, can you figure out how the passengers are moving, and be able to answer the question, do all the passengers have the same acceleration? We see gears used a lot, and obviously when you have gears or pulleys, and they're not always the same shape, but they're rotating about axes, and we want to know, how do their motions relate to each other? How does the rotational rate of one gear relate to the rotational rate of another gear? And we'll also look at that in this chapter. So just to start, defining some types of motion. So translational motion is basically the every piece of the body remains parallel to its original direction when it's moving. So it's kind of moving in a straight line in a plane. But if you followed the path of, say, some points on the object and those points traced out a curved shape, then that would be curvilinear translation. We're also going to be able to study rotation about an axis because in that case, all the pieces will maintain their same distance away from each other, and they're just moving along rotating about an axis, and all the pieces of the object then will move in circles, which their plane is perpendicular to the axis of rotation. So then if we put it all together, we could have the possibility of having curvilinear translational motion with rotation, and that would just be general planar motion. Okay, so now let's learn about some relationships and how we can talk about it. Now, in this picture, this is something you might have seen before with relative motion. We have a fixed coordinate system and then a translating coordinate system that is attached to our rigid body. We might locate 2 points on the rigid body, point A and point B. The position of A is given relative to the fixed coordinate system, and it actually is at the origin of the translating coordinate system. The idea that this system is moving at a, relative to the fixed coordinate system, of course. And then we look at position object B, or particle B, on our object. We can locate it relative to point A, and that's what this is, the position of B relative to A, and that's measuring it within the translating coordinate system. But we can also measure it relative to the fixed coordinate system as just R sub B. And R sub B, if you add your vectors, is equal to R sub A plus, it's basically equal to the position of A plus the position of B relative to A. But what happens when we think about, what happens if we think about velocity and acceleration? How do these relationships change, or what happens? So if we start our relationship, R sub B is equal to R sub A plus the position of B relative to A, and let's take the time derivative of this expression. Just sort of doing it in gory detail. And so now, the derivative of the position B with respect to time is just the velocity of B, and the derivative of the position of A with respect to time is just the velocity of A. But what is the derivative of the position of B relative to A? Well, this is a rigid body, so the position of B with respect to A does not change in time, and so that quantity is zero, leaving us with the conclusion that all the particles on the object are going to move with the same speed. We can then take the time derivative of this again to see how the accelerations relate to each other, and we'll find that they also, points A and B will also experience the same acceleration. And so basically we've come to the conclusion, or we've demonstrated, that all the points on a rigid body that are subjected to some sort of translational motion will have the same velocity and acceleration. Now, another type of motion that we want to look at is the rotation about a fixed axis. And a lot of this we're familiar with already. So the axis is vertical, the rotation axis is vertical. The direction of omega and alpha can be defined by the right-hand rule, where our thumb points along the axis when our fingers curl in the direction of rotation. If we follow a point P on the surface of the object, in some time it will be going through an angle, turning through an angle of theta, and we can use that to define angular velocity and angular acceleration, but the theta is how we define its position. Usually theta is defined in radians, and just remember that 1 revolution is 2 pi radians. So if we want to think about omega, omega is the derivative of the displacement with respect to time, or the position with respect to time. And so it's just omega is d theta dt. So we have that. And the angular acceleration is the derivative of the angular velocity with respect to time, which can also be expressed as the second derivative of the angular position with respect to time. So this should all be review for you in terms of these definitions. In the situation where alpha is a constant, and so we'll just call that alpha sub c to indicate that it's a constant, we can integrate these equations, this equation, and keep going to find a set of algebraic equations that will allow us to talk about how the angular velocity and acceleration and angular position all depend on time. And so this should look pretty familiar because we've done basically the same process for linear motion, but we're just doing it for angular quantities. And so we're separating our variables. On the left side, we're integrating over time, starting at time equals 0 and going to some arbitrary time t. On the right-hand side, we're starting at the initial angular velocity, omega naught, and going to the final angular velocity of omega, which both these values correspond, are happening at the same time. So alpha c times t, when we integrate, is equal to omega minus omega naught. So omega can be expressed as omega naught plus alpha ct. And so that becomes one of our expressions for the constant acceleration problem. And I'm just going to write that over here. And that's also equal to d theta dt. And so I can use that to integrate again. And if we just rearrange this, this should look really familiar. It basically has exactly the same form as as constant acceleration linear motion. We're just replacing the angular quantities. And then the last thing we want to do is if we want to eliminate time, what we can do is we can start with the definition of alpha, which is d omega dt, and use the chain rule. We did this with linear quantities. And so again, separation of variables. And it might look more familiar if we write it like this. Just rearranging our terms a little bit, multiplying through by 2. And so we have these three equations that govern constant angular acceleration. All right, so you might also remember that when an object is rotating about an axis, we can also talk about the linear quantities of velocity and acceleration for a point on that object. So for instance, if we're looking at point P, we want to know its tangential velocity of that as the object is rotating with a angular acceleration of angular velocity of omega. Remember that v is just equal to omega times r. But we can also find that if we think about it, it turns out that if we think about the direction of that velocity as well as its magnitude, it can be written as a cross product, where it's the cross product of omega, the vector, with r sub p, which is a vector that goes from the axis of rotation to point P. And so this is another way that we can write the velocity, and this is the tangential velocity of point P. And so this is something kind of new. We also might want to be able to write the acceleration. Now you might remember that there's two types of acceleration for an object. Point P is moving in a circle, so it can have tangential acceleration, which would be equal to alpha times r. And it also has a centripetal acceleration, which can be written as omega squared r, using the expression v equals omega r. You could also change that to v squared over r, in case you're wondering. So anyway, let's start with this expression and see if we can get some equivalent vector expression for acceleration, because acceleration is just the derivative of the velocity with respect to time. And so using the chain rule, not the chain rule, the product rule, we see that this would be alpha cross r sub p plus omega cross v, which can also, we can replace v with omega cross r. And so I'm going to write it down here, just easier to work with. This represents the centripetal acceleration, and this represents the tangential acceleration. So the total acceleration is the sum of these two components, which we've now been able to write in a vector format. Something for us to remember, that we can use that later. Oop, I don't know that. Now, the last thing that I need to remember is when I have gears interacting, like how do I relate their motion to each other? You know, it seems clear that they can't rotate at the same rate. So what is true? Well, what we find is if we take a point on either gear, both of those points have to be moving with the same velocity. And so I'm going to just sort of write, so v sub a is equal to v sub a prime. But that's a tangential velocity. So for the left-hand gear, that's actually going to be a product of the radius times its angular rotation rate, which is, I'm going to call omega b. And on the right-hand side, it's the radius of that gear times its rotational rate. And so that is how I'm going to relate those two. And it also turns out that the two are going to have the same acceleration, but tangential. They have to have the same tangential acceleration. They're not necessarily going to have the same centripetal acceleration. And see if you can convince yourself why that's true. That means that r sub b times alpha sub b is going to be equal to r sub c times alpha sub c. And so these are two relationships we can use for gears. A lot of this right now is just sort of background information that you can use then to apply to some more realistic problems. And that is it for the first part of chapter 16.